right, my friends, in our ivory book, we are going to be on page, which page is it? We're going to be on page 102, page 102. So hopefully you guys took a look at this yesterday. So we're not going to spend a lot of time on it. This particular type of diagram, we're going to go through just a little bit of terminology. This particular type of diagram is called a potential energy diagram. Page 102. And you'll notice that, of course, on our y-axis we have potential energy, but on the x-axis, we have direction of reaction. We could also write progress of reaction. That would be another alternative label for the x-axis. We could also label it reaction proceeds. Okay, and one thing that makes me happy about this diagram compared to the one from last day is that the change in potential energy, the arrow actually starts at the correct place and finishes at the correct place. So if I was to draw like a little dashed line here, you can see that the arrow, this downward pointing arrow, ends where the products are. It doesn't sort of end halfway down. Because the potential energy is decreasing, the arrow should point downward. Okay. And if the potential energy is decreasing, how is it that the potential energy is decreasing? Why is the potential energy decreasing? How has that come about? Did we throw it away? What happened to that potential energy? It was converted into kinetic energy. Okay, so basically the potential energy has been transformed into kinetic energy, and in the form of kinetic energy it is then released into the surroundings. So that kinetic energy is then released from the system into the surroundings. And what quantity measures kinetic energy? Temperature. So if the kinetic energy is being released, what's happening to our temperature? Temperature is increasing. Okay. Now, do we remember from yesterday we were talking about entering a building? And do you go upstairs or downstairs when you enter a building? You go up the stairs. So your endothermic potential energy graph should go up. Well, when you're exiting the building, normally you have to go down the stairs. So an exothermic reaction, the potential energy should go down. And you can see the potential energy is going down in this reaction. All right, and I think that is about it for this one. We are now going to go on to 6.4b. And there's not actually that much new in here other than some new vocabulary that we're going to apply to what we've been doing. And our first vocabulary word is the title. It is enthalpy. And for grade 11, and in fact grade 12, enthalpy can be thought of as the chemical potential energy. That is not actually the definition of enthalpy. So if you go off to university and they're like, no, it's not the chemical potential energy, I didn't lie to you. I'm just saying this is a good way to think about it. The actual definition for enthalpy involves a mathematical equation. And let's see what it is. Enthalpy. I always have to look it up because it's quite specific. Enthalpy, a quantity defined by the relationship H is equal to E plus PV. The enthalpy change delta H for a reaction that occurs at constant pressure is the heat evolved or absorbed in the reaction delta H is equal to QP. Anyone want to learn that definition, or do we like enthalpy being chemical potential energy? Yes. Okay, so that's what we're going to do with it. Let your university professors explain what the real definition of enthalpy is. Okay. Now, the other thing is, I guess they ran out of letters. E is taken by energy, so we can't use E for enthalpy, so they took a letter in the middle of the word. So they took that H. Okay, so the symbol for enthalpy is H. Are you guys familiar with the symbol delta? What does delta mean? Change in, okay, so change in. And usually what we are concerned with when it comes to enthalpy is the change in enthalpy. We're looking at the change in potential energy. Did the potential energy increase or did the potential energy decrease? So change in enthalpy is given the symbol delta H. So if we have an endothermic reaction, kinetic energy is transformed into potential energy. Therefore, the potential energy is increasing. So our potential energy increases. Guess what? Potential energy is the enthalpy. Those two mean the same, at least for the purposes of chemistry 11. So if the potential energy is increasing, the enthalpy is increasing. And if something is increasing, is the change positive or negative? Positive. So the change in enthalpy is positive. Okay, so the enthalpy increases, change in enthalpy is positive. That's an endothermic reaction. In an exothermic reaction, we're taking some potential energy and transforming it into kinetic energy. Therefore, our potential energy decreases. And since enthalpy is potential energy, the enthalpy decreases. And if something is decreasing, is its change positive or negative? negative, okay? Since it's decreasing, the change is negative. So the delta H is negative. So the first word that we've learned is enthalpy. The symbol is H. Change in enthalpy is delta H. The heat term. So here we have a reaction where we're having some gasoline, which is mainly C8H18, and it is undergoing combustion. And without really thinking about it too much, if we are burning gasoline, is that an endothermic or an exothermic reaction? Burning. Exothermic, because guess what's coming out? Heat, light, energy is coming out. Okay, so this is an exothermic reaction. The chemical reaction produces heat. Now, if a reaction produces heat, would you expect for heat to be a reactant, or would you expect for heat to be a product? A product. So sometimes if we don't know the exact amount of energy, instead of writing a specific number, like 10 kilojoules, we will just write heat. So you can see here is our reaction arrow. Over here, these are our reactants. Over here, these are our products. And on the product side, we have the heat term. Now that heat term is actually kinetic energy that is released from the system and moves out into the surroundings. Now, if we have released kinetic energy, what's happening to the temperature? It's getting higher, yes? So we have more kinetic energy, therefore the temperature is higher. So if we have more kinetic energy, in the products, what must have happened to the potential energy from reactants to products? What was the change in potential energy from reactants to products? So we have, going from reactants to products, we have kinetic energy is increasing. What's happening to the potential energy? The potential energy has to be decreasing, which makes sense because what do we remember about the potential energy diagram? For an exothermic reaction, it goes down. That enthalpy, the potential energy, is decreasing. Okay, so that kinetic energy term is often referred to as the heat term. Okay. So I've just rewritten this here so we can refer to it as we're looking at the potential energy diagram. And you'll notice that on the y-axis, I can either label it potential energy or I can label it with that new word, enthalpy. Yes? The unit, regardless, is kilojoules, or sometimes you'll see it as kilojoules per mole. If we're doing it next year, we'll be all about the kilojoules per mole. This year, if you just write kilojoules, that'll be fine, okay? So here we have our gasoline and our oxygen. Are those the reactants or the products? The gasoline and the oxygen. Those are our reactants, yep. And what can you say about their potential energy? Is it high or low? Potential energy is high. Down here, we have our products. And the potential energy is low. And you know what else is a product? The kinetic energy. And if you are asked to label the change in enthalpy, you can see we have labeled it right here. We're starting at the level of the reactants. You see how we've drawn that dashed line over from the reactants? And we go directly from that dashed line all the way down to the bottom. That is our delta H. What does delta H stand for? Change in enthalpy. What is change in enthalpy? It is the change in what kind of energy? Potential energy. Change in enthalpy is the same as change in potential energy. And since it's going down, the change is negative. Okay, so delta H is negative. Since delta H is negative, what kind of a reaction is this? Endo or exothermic? It's exothermic. When delta H is negative, we have an exothermic reaction. When we have an exothermic reaction, what happens to the temperature? The temperature must increase. Now, why is that? Yeah, in an exothermic reaction, potential energy is converted into kinetic energy. The kinetic energy then exits the system. It makes the particles move faster. And therefore, what happens to the temperature? The temperature goes up. So there are two ways to show in a reaction that a reaction is exothermic. We can take the heat term and we can write it in the, where should the heat term go? Should it go in the reactants or the products? It goes in the products. So the heat term goes in the products. Kinetic energy is produced. However, sometimes we're going to write this as an equation without the heat term in the reaction. We can write it actually a different way. We can write it with the change in enthalpy written off to the side. Okay, so we can write our change in enthalpy, and in this case, the change in enthalpy is negative because our potential energy decreased. The potential energy, in other words, the enthalpy, decreased. So we can say three things for an exothermic reaction. Number one, where does the heat term go if we put it in the reaction? Heat term goes in the reactants or products. Is energy being consumed, or is energy being absorbed, or is energy being produced? Kinetic energy. Okay, because remember the heat term is the kinetic energy, and it's being released, it's exiting the system. And so if it's exiting, if we've got our reactants over here and we've got our arrow, where would something that's exiting the reaction go? Would it go in front of the arrow or after the arrow? After the arrow. Something that is exiting goes after the arrow. So therefore, the heat term has to go in the products. Second thing is that the change in enthalpy, delta H, is that positive or negative? Negative. And then the third thing is if we have our potential energy diagram, which way does the graph go? It goes down. So those are the three things you should know about exothermic reactions. The heat term goes in the products, delta H is negative, and the graph goes down. Can you guess what it is for an endothermic reaction? Oh my gosh, it's all the opposite. The heat term will go in the reactants because that kinetic energy is being absorbed and turned into potential energy, which makes the potential energy go up. Oh my gosh, the graph goes up, which means the delta H is positive. You want to do that one more time? In an endothermic reaction, heat is being absorbed, which means kinetic energy is coming into the reaction. What is the chemical reaction doing? It is then transforming the kinetic energy into potential energy. So what's happening to the potential energy? It goes up because kinetic energy is now being transformed into potential energy. So now we have more potential energy. And if it's going up, what was the change in enthalpy? Positive. Okay, so we've got an example of that right here. Here we have the heat term is in the reactants. So this is our kinetic energy. And you'll notice down here, it says that it is absorbed from the surroundings. And then the kinetic energy is, what happens to it after it's absorbed? It's converted into potential energy. Excellent. Therefore, what's happening to the potential energy? The potential energy is increasing. What's happening to the kinetic energy? The kinetic energy is decreasing. We've converted kinetic into potential, so we don't have as much kinetic anymore. Now, kinetic energy, what result does that have? That means that the temperature goes down. And if the potential energy is going up, what does that tell us about our change in enthalpy? The change in enthalpy is positive. And that means that our graph is going to go up. That's a positive change in enthalpy. So we can take a look at this actual little reaction here. We have our reactants. We have our products. The kinetic energy is absorbed, then transformed into potential energy. And that's why the potential energy goes up. I know I'm just saying the same thing over and over again. I do understand that. But it can be a little bit like mind bending when we first do this. So sometimes hearing it more than once is good. Since delta H is positive, what do we know about the reaction? The reaction must be endothermic. And therefore, what's going to happen to the temperature? Tell your partner what's going to happen to the temperature in an endothermic reaction. The temperature must decrease. Because even though we absorb that kinetic energy, it then gets transformed in potential energy. Therefore, we don't have as much kinetic energy as before. Okay, let's try a little summary of our, here's a summary of our endothermic reaction. So in an endothermic reaction, the heat term is in the reactants. Delta H is positive, and the graph goes, which way does the graph go for endothermic? Up. Why did I write end? I should have wrote endo. Graph goes up. So if you know those three things, you've actually got a significant chunk of the first unit of Chemistry 12 under your belt. Look at that. Not a significant chunk. Well, you know, like a bit of the first unit of Chemistry 12. All right, we're going to leave this for now, and we are going to go to your other workbook, Blue Book. And I'm going to give you guys one of these.
I felt some water bottles.
Yes, you may.
Last call. Anybody? Water bottles?
All right, so you can refer to this at any point. Obviously, during a quiz or test, you will not be allowed to have this, but it's a good tool, okay? Now, if you're like worried about passing the course and you come and talk to me, you might be able to use it during a quiz or test, but that's gonna be like for people who are kind of like, uh-oh, right? You are not gonna get to use it, okay? Just telling you right now. Yeah. Huh? Rex, no, you don't get to use it. All right. Anywho, this is, it's just there for your reference. We will be referring to it fairly regularly. We are going to go to, I think it's 7.1c. Yes, it is. So this is on page 14, 1-4. All right, and last day you did some math using the molar mass. Today we're going to be focusing on that middle part of the chart. So if we have a volume of solution, like here, volume of solution A, we can find the moles of A. And what do we use to do that? We use the molarity. What are the units of molarity? Molarity is measured in moles per liter. So we can put that in over on the other side as well. If we're going from moles to volume, we would also use molarity, so we can fill in moles per liter. That has to be given to you in the question, okay? You cannot, unless the question was find the molarity, if you're using it as a conversion factor, it has to be given to you in the question. Now, last day we were using the molar mass. What is the unit of molar mass? Grams per mole. Where do you find those grams per mole? You find those grams per mole on the periodic table. And finally, the big piece, the big picture of stoichiometry is all about this mole ratio. Where do we get the mole ratio from? That's from the coefficients. I wrote too big. Coefficients. Okay, so we're going to be focusing on that middle section today. A is going to be your known substance, and B is going to be your unknown substance. Did I manage to do this? No, I did not. Okay. Alrighty. We have, oops, thank you. Couple of things, molarity, when it's given in the question, you're always going to rewrite molar as moles over liters. And you're always going to convert volume into liters. So you're going to need to take your milliliters and convert them into liters. All right, let's take our question here. H2 is produced by the reaction of 118.5 milliliters of 0.8775 molar solution of phosphoric acid with chromium according to the following equation. So we have an equation here. That's nice. And we want to calculate the number of moles of H2 gas produced. In this question, who is the unknown? The H2 gas. So that is our unknown. Therefore, is H2 substance A or is H2 substance B? H2 is substance B. That means that our other substance in the question, what's the other substance in the question? That would be our phosphoric acid. That's going to be substance A. That is our known, and it is substance A. Now, I don't know if you guys remember, but in the mole unit, when you read something like 118.5 milliliters of an 0.8775 molar solution, this many milliliters of that much molar. Do you remember what of means? Of means times. So we're going to be multiplying 118.5 milliliters times 0.8775 molar, but before we do that, we need to rewrite the milliliters and rewrite the molar. So let's take our 118.5 milliliters, and I would like you to, in your head, convert that into liters. And I'm going to give you two choices. And I'm going to tell you right now that if you cannot immediately tell me which of those is correct, then you should be using a conversion factor to convert rather than just moving the decimal. If you can tell me immediately which of those two is correct, then you can just move your decimal place. But if you're like, I don't know, then you should be using the conversion, 118.5 milliliters. You need to cancel milliliters and find liters. How many of one is equal to the other? There are 1,000 milliliters in 1 liter, which means you're dividing by 1,000, which means you're getting that. Okay, if you cannot do that in your head, then you should be using the conversion factor, but if you can move your decimal place fine, then that's great. Okay, so we have now found milliliters, we've changed it into liters. But when you're doing stoichiometry, it's not really good enough to write 0.1185 liters. We should also be writing down what that is liters of. What is the substance? What substance is associated with 1185 milliliters? 118.5. That is the phosphoric acid, right? Because it's like blah-de, 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 blah phosphoric acid. Okay? So we're going to write down that we have that many liters of H3PO4. The other information that we're given in the question is this 0.8775 molar. And remember, molar means moles per liter. So we're going to rewrite that down here. We're going to write 0.8775 moles per liter. What have I forgotten? The substance. That is moles of, what substance are we dealing with here? Again, it's the H3PO4. Okay, because if you read the sentence, it's like that molarity of phosphoric acid. Okay, so that again is H3PO4. Okay, so we've got that. We've got our stuff set up. Now let's take a look at our little chart and say we are starting with, what are we starting with? We're starting with the volume of the solution. Is there any choice for starting with the molarity? Molarity? No. Molarity? No. Molarity? No. Your initial quantity is always going to, if you've got a volume and a molarity, your initial quantity is the volume, not the molarity. The molarity is the conversion factor. Okay? So let's go over here. Let me find where I put it. There we go. So this is our initial quantity. And this is our conversion factor. And we are starting with substance A, which is H3PO4. Yes? What is step 1 of any stoichiometry conversion? Find moles of A. Yes? Convert to moles of A. So step 1, find moles of A. And if you remember, substance A is H3PO4. So we are going to take our 0.1185 liters of H3PO4 and we're going to convert it into moles of substance A, which is H3PO4. So that's step 1. The second step in any stoichiometry problem is going from moles of A to moles of B. Or we could make it even simpler. We could just say find moles of B. Yes? Find moles of A, find moles of B. Let's do that. Find moles B. All right. Now, who is B? Let's go back to our question. Remember, B is the unknown, and that was the H2. That was our unknown. So we're going to go from moles of H3PO4 to moles of H2. And then at that point, we ask ourselves, does the question ask us for something else? Does it ask for mass or volume of H2? And the answer is no, it just wants moles. So we get to stop right there. Not bad. Okay. So here we are, ready to go. This is our little map. And we're going to start with 0.1185 liters of H3PO4. And we want to cancel those liters of H3PO4 and find the moles of H3PO4. Moles per liter. Should I use 22.4 liters per mole? No, why not? What is 22.4 liters per mole? This is only for gases. Do we have a gas? We do have a gas, but it's not the H3PO4. The H3PO4 is a, if you look at it, it says it is a solution. Okay, the H3PO4 is a solution, so you don't want to use 22.4 liters per mole. So it's only for a gas. H3PO4 is a solution. So if we're not doing 22.4 liters, we can always go back to our little sheet here and say, oh, I'm going from volume of a solution to the moles of A, and so I'm going to use moles, I'm going to use the molarity, which, oh, guess what, was just given to me in the question. Look, it's right here. Okay, we have 0.8775 moles of H3PO4 per liter. And now we are going from moles of H3PO4 to moles of H2. Now, when we have moles of one substance and moles of the other substance, where do we go look? We go look at our coefficients. Okay, and what are they? I think we have we can go look them up. There's our reaction there. Oh, okay. We've got a 3 in front of the H2 and a 2 in front of the H3PO4. I could have predicted that, but that's okay. We had a 3 in front of the H2 and a 2 in front of the H3PO4. We do that math and we get, to be honest with you, I don't want to do the math. So I'm going to go, oh, look what, guess what? All of this was done here for you, right? All of that work that we just did on the side, it's here. It even tells you that liters will always be the initial quantity and the moles per liter will always be the conversion factor. So everything is here and we can look, here's our work. It's all laid out beautifully. It's nice and tidy. Our smallest number of sig figs is 4 sig figs, so our answer is 0.1560. That's at the bottom of page 15. Is good? Ding. If you feel really confident, you can go work on page 18 right now. For the rest of you, I'm going to do one more example because it shows how to get to a volume at the end step. Okay? Up to you whether you follow along or whether you choose to do start on the work on page 18. Okay, so that's your homework there. The reason this question is a little bit trickier is that I actually have two substances here that have quantities associated with them. I know that I have 0.300 molar NaOH, and I know that I have 56.8 grams of H2SO4. And sometimes it's hard to figure out which of those is the known and which is the unknown. From reading that question, can you tell me, NaOH or H2SO4, who is the unknown? Read the question. The NaOH is the unknown because guess what it says? What volume of the NaOH? That means that my NaOH is substance B. the unknown. And that means that H2SO4 is substance A. Okay? What is one of the first things you should do when you see that capital M? Rewrite it as, what do we rewrite capital M as? Moles over liters. So we have 3.00 molar, and you can see it's actually done here for us. That molar becomes moles per liter. And don't forget, whenever you have a unit, it should, in stoichiometry, also have a quantity beside it. So that is moles of NaOH per liter. Is this our initial quantity, or is this going to be a conversion factor? That's going to be a conversion factor. It can convert between moles and liters. Or liters and moles. Okay. So now let's see if we can figure out a map of this problem. We're going to start with substance A. We are starting with 56.8 grams of H2SO4, which is substance A. Step 1, find moles of A. Oh, that's easy. So we're going to go, okay, I'm going to go from grams to moles, and substance A was H2SO4. Step 2, find Step 1 is find moles. Step 2 is also find moles. But in this case, in step 1, we found moles of A, which was our known substance. And in step 2, we're going to find moles of B, which is our unknown substance. So who is the unknown in this question? Go back to the question, what volume of NaOH? NaOH is our unknown. So we're going to go from moles of H2SO4 to moles of NaOH. And then you have to ask yourself, what does it actually ask for in the question? I want the volume of NaOH. So now we're going to go from moles to liters of NaOH. What conversion factor do we use to go between grams and moles? Grams and moles, we use the molar mass. What's the unit of molar mass? Grams per mole. What do we use to go between moles of one thing and moles of the other thing? We use the mole ratio, which comes from the coefficients. And now NaOH, we know that NaOH is a solution. We can go back and read in the question, it says solution. Should we be using 22.4 liters per mole? To go between moles and liters? No, only for gas. Because NaOH is a solution, we will not use it that way. What do we use to convert between moles and liters of a solution? Well, if you forget, you can go back to our lovely little diagram. And what do I use to go between moles and liters of solution? I use molarity, and molarity has to be given to you in the question. Okay, I've lost it. It's totally gone. Where is it? Okay, there it is. Okay. So we're going to use the molarity. So we have 56.8 grams of H2SO4. The molar mass, I happen to remember it from this morning, so I'm not going to actually go to the periodic table and calculate it, but you could. It is 98.1 grams of H2SO4 per 1 mole. 1 mole of what? H2SO4. We have successfully done step 1. Step 2, convert from moles of H2SO4, so put that on the bottom, into moles of NaOH. Anytime you're converting from moles to moles, that is from the coefficients. So let's go back to our reaction, and we have 2 NaOH for every 1 H2SO4. So there's 2 NaOH for every 1 H2SO4. And finally, for our last step, we need to cancel the moles of NaOH, and we need to find the liters. And we're going to be using the molarity, and we were given the fact that the molarity is 3.00 molar. Remind me, what does molar mean? Molar means moles per liter. We've already written it down somewhere else, but I'm writing it down again because it's worth repeating. This is 3.00 moles of NaOH per liter. Some of you on your moles test tried making up conversion factors, and you would have had a comment from me, please don't make up conversion factors. You can't do that. You can't just say 1 liter is 22.4 moles. Oh, I know that number. 1 mole is 6.02 times 10 to the 24 liters. 6.02 times 10 to the 23 liters. Like, there's just random numbers came out of nowhere. You need a number that is either a conversion factor that you know or something that's given to you in the question. So this one, 3.00 moles for every 1 liter. We do the math on that. And again, we don't need to do the math because guess what? The math is already done. Let's check and see, because I got a different answer this morning. 56.8 divided by 98.1 times 2 divided by 0.3 equals, oh, hang on, is it 0.3 or is it 3? Oh, that's why it's Oh, is it 3 molar or 0.3 molar? 0.3 molar. Did I write 3 molar or did I write 0.3 molar? Oh, molar. 0.300 molar. I'm so sorry. Screwed up on my decimal there. Okay, so that would be 0.300 molar. But it's written correctly here. And so when we do that, we get 3.86. I would like you to see if you can convert that into milliliters, just to check your math skills. And I'm going to give you two choices. If you can tell me immediately which of those is correct, you can just move your decimal. And if you're looking at it going, I'm not sure which of those is correct, you, if you were asked to convert to milliliters, will go 3.86 liters times, I need to cancel liters and find milliliters. There are 1,000 milliliters in 1 liter, which gives me 3860 milliliters. Okay, so if that's happening in your head, that's great. If not, please do this until it becomes automatic. Okay? So homework is page 18 in the blue book, page 103 in the ivory book. Tomorrow we're going to do a demonstration of a titration so that next week, no, not next week. Next week we're like learning things. We're learning things. But the week after that, on Monday you have your test, and on Thursday you will do, on Wednesday you will do the titration. And then on Friday, my marks are due at 9 a.m. to the office. Your grades will be posted. So what are we doing on Friday? Nothing. So I will be religiously taking attendance. You absolutely must be in this classroom. Okay? I am telling you officially as your teacher, because otherwise I could get in deep trouble, that you have to be here. Okay? And if you did not understand that, then you need to get somebody to explain it to you. Every year I have one person and they're like, what? They were like listening to your AirPods or something and they're like, what just happened? Right? So. Okay, so working on that. And then it's Friday the 23rd is the day when I will be doing nothing with you.
Is this a typo? Could you put mold instead of
Oh, that's a typo there. Yes, thank you. I need to fix that. Yes, if you didn't notice, there's a typo here. This should have been grams, not moles. Okay, that's at the bottom of page 16. Fix. Combination of the HCl. Yeah, it is a double replacement, yes. Yeah. I'm going to quickly run to the washroom, but I'll be right back if you have any questions. 5-day weeks are killing me.